That should make sense. Right, so work and force. How does it work? How does the work work? I was trying to avoid the puns on this thing. So you've got a force on an object. And when you force on an object, what does Newton's first law say? It's going to? Why is it not working now? I want to go backwards. Oh, that's not good. Okay, won't go backwards. Anyway, so Newton's first law, second law says, what happens if you exert an unbalanced force on an object? It will accelerate. Where? In the direction of that force. So you've got a force on this object that accelerates to the right, and it will move a certain distance. All right. Now you might remember from grade 8. I don't know if you remember, but in grade 8 we did work force and power just to a small level. And the definition you got was work done is equal to force times distance. Right? So now we developed that a little bit. It's work is equal to force times displacement. I'm going to just get rid of the thing there. It's force times displacement. So you've got F times delta X. Right? And there's your simplest little definition of work. And that's how you would calculate it. You'd need to know how big is the force, how many newtons, how big is the displacement, how many meters, and then you're going to have so many newtons times so many meters, and you're going to get an answer, right? But that's only if they're all in the same direction. Now it needs to get a little bit more complicated than that, right? So what happens if I pull the object like this? It's still going to have it's still an unbalanced force. That's assuming that there's no friction at this point, right? So it's still going to move, still going to accelerate in that direction. So the displacement is now in that direction, but the force isn't in that direction. So now you can't just use the force. The force is applied at a certain angle. So now you've got to say, all right, I need to use the x component of this force. Now you guys know how to work out components, don't you? Yes? So you only have to use the x component. You have to use the component of the force in the direction of the displacement. So we're using the x component because the displacement was in the x direction. Does that make sense? Good. Yes, Trey.
So the PowerPoint isn't working on mine. Can't download it. Go to Teams.
No, get it from Teams. I took it off the intranet. It's on Teams. So how do we work out the x component again? F cos theta. Alright. So cos theta is going to be adjacent of hypotenuse, which is adjacent is fx, and hypotenuse is f. So if you change that around, you're going to get f cos theta. So work done is the x component of the force times the displacement. So we've got fx times delta x. Now here you've got a way to work out fx. So we can say, alright, since cos theta is f over f, fx is going to be x cos theta, and therefore w is going to be equal to fx times delta x, which is f cos theta times delta x. Okay. Now they normally change that around and they write it like this. They split up the f and the cos theta and they write f delta x cos theta. I don't know why we do that. It's become sort of convention, and it can be a little bit annoying. You can't forget that the f and the cos theta are linked. The cos theta is the angle between f and delta x. Alright? So it's a few little things you put in there, I think. Or was it all filled in? All filled in. Okay. So that covers all the directions of f and delta x. All you must remember is that theta is the angle between f and delta x. Alright? So here we go. There's your definition of work. It's product of the resultant force applied in direction of motion. And the formula is F delta x cos theta. So there's your setup. You've got delta x. The unit of work obviously is joules. It's force times meter, so that's newtons times meter, so it's 1 newton meter. That's what a joule is. That's how we work out Fx. And then that leaves you with your formula. which is F delta X cos theta. Couple of little points there to note. Work is classed as a scalar quantity. It's not classed as a vector. Even though you're going to see, when we get to discussion things later on, the direction in which the work done is important actually. Because you can get negative work. And I know you're going to start thinking, but how can if it's not a vector, how can you get negative work? And it turns out you can. But we'll still talk about it further. Alright, now I'm going to look at this in a bit more detail in a minute. If the forces in the space are in the same direction, then theta is naught, so cos theta equals. What's cos of naught? 1. Cos of naught is 1. So if they're in the same direction, cos of naught is 1, and so the formula just reduces to F delta X. Okay. Because the X component of F is F. Okay. Good. Can I move?
No, sir.
Okay. Yes? So this point is easy. Now we need to just refresh your mind about cos theta. Right? So what I did is I put a little spreadsheet where here's the possible values of theta going from 0 to 360, and this is cos of theta. Yeah? So what happens? Cos of 0 we said is 1, and then as theta gets bigger, what happens to cos? It decreases from 1. So there's the graph. It says 1. As the angle gets bigger than 1, cos theta decreases till it becomes 0 when theta is 90. Then when theta goes past 90, cos becomes negative. See, these values are all negative. Goes through negative 1 when the angle is how much? No. 180. 180 is negative 1. Okay? And then it becomes 0 again at 270. Right? So there's 2 points where, actually in a 360 cycle, there's 3 points where cos theta is going to have a magnitude of 1, right? And there's 2 points where it's going to have a magnitude of 0. And obviously, if the formula is f delta x cos theta, if you multiply by cos theta, it becomes 0, then what happens is the work? 0. So these 2 points, when theta is 90, when theta is 270, the work done will be 0. But when theta is 0, or when theta is 180, or when theta is 360, well that's the same point really, then the work done is just equal to F delta. Happy? So there's your formula. So let's have a look. Alright. Okay, we've actually got it. I don't think you need to do this. I did this twice without realizing that we've done the first one. So obviously this is delta x. There's your also we read all that. You don't have to go through these. Alright. So let's have a look at this. What happens when the angle increases? If you put in an object with a small theta, alright? What do we know about the value of cos theta? It's close to what?
1.
It's close to 1. Okay? So you're going to have quite a large value for work. Let's just go all the way through this and then you get to your one. So here, when you've got a small value of theta, then because cos theta is close to 1, x is large, and so you've got a large amount of work done. Now, as the value of theta increases, what happens? Well, it's going to decrease further. So, as you increase the angle of this force, the work done in the x direction is going to be less. It's going to move us a smaller distance. And the more you increase that force, the less distance it moves. And so the less work you do.
So the force there.
And the more you increase the angle, the smaller your x component of that force becomes. And so the less work you're actually doing in that direction. So as theta increases, cos theta gets smaller than 1. And so the x component decreases. Right? And when the x component decreases, then the work done decreases. Now, I've actually written here that delta x decreases, but actually delta x might decrease, but it's actually fx that's decreasing. The x component of the force is decreasing. Now, with a smaller force, would you fall at a smaller distance? If there was friction, probably. You have a smaller acceleration anyway. So you'll probably move less distance in the same time. So those both might decrease. Trey, you got a question?
Yes, so work is directly proportional to the, inversely proportional to the angle of the
Yes. Only up to 90 degrees though. Because after 90 degrees, so it's bigger. And I don't know if it's directly inversely proportional, if you know what I mean. If you double one, it's over half. I doubt it if it's curved. So it may not be, like you double the angle that work hard. I'm not sure what that is. Yeah. Okay. Any questions? Let's go. Good. What happens when the angle equals 90?
So, 0.
Now, this can happen two different ways. The object can be moving across the friction in the surface, and a satellite moves around the planet. Right? In either of those cases, if the object is sliding at a constant velocity, then there's no force pushing. So then there's no force in the direction of the motion. The only force on it would be, if the force is vertical, then, like a normal force, for example, or any other force that's being pulled straight up. If it's moving this way, but the only force on it is up, the angle is 90, so the project would be 0, and so the work done by that force would be 0. If you think about a planet going around the Earth, a planet going around the Sun, or a satellite going around the Earth, or the moon going around the Earth, the only force on it is the force of gravity. But that is 90 degrees to the displacement of the object at any point. So that force of gravity isn't doing any work on the object because the object is not moving in that direction.
So the object isn't moving like directly, it's not doing directly force, it's moving like this.
It's moving at 90 degrees to that force all the time. And they're both changing the angle.
Yeah.
So because cos theta is 0 in all these cases, because cos theta is cos of 90 and that's 0, you're multiplying by 0 in this equation, and so you've got no work done. When theta is 90 degrees, there's no work done. Please don't forget it. I know when you look at it like this, it looks dead simple. You're like, oh, okay, that's easy, but when we give you a question, there's a whole lot of information provided and all that kind of stuff, it's easy to miss it. Also remember, listen to what I'm saying. I'm saying the work done by that force. There can be more than one work done on an object. Okay? Work is done by any force that moves at a certain distance. So if there's two forces moving it in a distance, in both the directions, they both move. So you can have, for example, an object moving with friction on it. And the force moving it is doing work, and friction is doing work. Or when you pick up something, if you pick up any object, you are exerting force on it, but gravity is also exerting force on it. Both you and gravity are doing work on the object. So not only is there work done by lots of different forces, there's also, can be therefore, a net work done. Now, let's just talk about this business when the force gets bigger than 90. If the force gets bigger than 90, didn't we say cos theta becomes negative? That cosine becomes negative, you multiply the negative into the equation, and so what are you doing? You've got a negative work. Now, how can that be negative?
Going opposite direction of the state.
Think about you pulling, your dog's taking you for a walk, okay? And you are pulling back on the thing. Now, if you weren't pulling back, what would the dog be doing? Running. So you are slowing down the dog's motion. You are reducing its kinetic energy. Because you're reducing its energy, you're doing negative work on it.
So,
Yeah.
how do you work out the distance of stopping something or slowing something down?
Well, you can just use equations of motion. The delta x between when the VF becomes normal. So in a case like this, you have got a negative work. Why? Where does that minus come from? It comes from this angle being how much? Like more than 110. Anything bigger than 90. Any angle between 90 and 180 is going to have a negative value of cos. And so that makes the whole thing negative and you get a negative work. And you must get that in the calculation. And you must say, okay, this is negative work. You're the one who's going to get right. So that will be a similar case as to when you're doing calculating work done by friction. Yes, please.
It won't always be that case. If I'm putting something back, it might come back with.
Oh, yeah, but then its displacement would be in this direction.
So it will be for negative.
No. Because if you, that means you'd be actually pulling it that way. You'd be pulling it in the direction of the delta.
Yeah, so
So that your theta wouldn't be above 90, it'd be less than 90.
if I'm putting it like this, then
Yeah, but if you remember, the angle is the angle between the direction it moves and the force. So if you're pulling it this way, right? If you're pulling it this way, but it's moving that way, then this is your angle, and it's bigger than 90, so it's negative. But the minute it stops moving that way and starts moving this way, then this is your angle. Less than 90, it's positive. The minute it moves in the direction that you're pulling it, slightly,
and then the delta x will
yeah,
also be
positive.
So I don't understand how it's possible to scale quantity.
Okay, don't worry about that now. We're going to discuss it more and more when we do questions. All I'm saying, all you need to know about that is only to put a direction next to it. But you do need to know which force is causing the work. Okay. Yeah.
If you both pull it and don't move it forward,
Then delta x is 0.
that's the way
No work. No work done. So if I stand here holding something very heavy all day and I don't move it in any direction, technically I've not done any work. Technically. What you have done is you've got to work on the muscles. Because in order to hold something, the muscles have moved. So you've done internal work. But you haven't done any work on the object. Because you haven't moved it. Alright, so there we go, it's bigger than 90. Okay, so let's have a look at kinetic energy quickly. What time did we finish? Okay, quarter two. Now you should remember this from grade 10. What is kinetic energy? It's energy's capacity to do. So what is energy? Energy is capacity to do what? Work. Energy is a scalar quantity, has the same unit as work. What's the unit of energy and work? Joules.
No, what's this?
Therefore, it's like therefore. When energy is transferred, what is done? Work is done. And if an object is accelerated from rest, so now let's consider an object that's accelerated from rest. Okay? So let's say you've got a mass here, and you exert a force to it. Newton's second law tells us that if you exert an unbalanced force to a mass, it will accelerate. So here's the object accelerating in that direction. So let's have a look. Let's take the definition of work and combine it with Newton's second law and see what we get. There's the object. I exert the force. Watch what happens. It accelerates. And it's got an initial velocity and a final velocity, and it's got an acceleration. You agree? So, Newton's second, the definition of work says W equals F delta X. Because they're all in the same direction, we can ignore the angle. You agree? Now we know Newton's second law says F equals ma. So we can put ma into there, you agree? Yeah? So W equals ma delta x. But what is acceleration? Isn't it the change in velocity over time?
Yes.
So it's Vf minus Vi over delta t. And we know that there's an equation that gives you Vf equals Vi squared plus 2a delta x from equations of motion. Have you done this?
Those are the answers.
One. I've got enough things to worry about, I don't need any more. So, if you put those values in, because Vi here was naught, yeah, it was standing still. So if you put those values in, this disappears. Vf we're going to now call final velocity V. So this equation is going to become V is equal to 2a delta x. So we can rearrange it, so get delta x, take 2a to the other side, delta x will be V squared, I'm going to call Vf V, delta x will be V squared divided by 2a. All happy with that? Yeah? So now we can put this into this equation. Why would we do that? So W equals ma becomes W equal to ma times V squared over 2a. The a's cancel out, do you agree? And then you get mv squared over 2, which is half mv squared. That's the equation. You don't need to know how to divide. I'm just showing you. Okay? So that is the energy of movement. Energy of movement is the same as the work done to cause that movement. Which makes perfect sense. You agree?
So is it like MC squared? Is it just like
No.
Why is that?
Equals mc squared. That will be the energy required to accelerate the mass m to the speed of light. No, because I've got a half, so it's not an energy formula. It's not half mc squared. I've seen it, I've done the derivation for that one. We did it in the second year physics at university. It's a very interesting calculation. So what you do is you use massive, it's a relative motion calculation working in two different reference frames. So you've got velocity of the object in this reference frame and velocity of that object in the other reference frame, and you've got a massive, huge equation. And then you apply Einstein's second assumption, or second postulate for forget what he calls it, but the second postulate is that the speed of light is a constant to all observers in the reference frame. And so you've got the speed of light everywhere in the thing. You've got the speed of light in one reference frame, speed of light in another. You make them all equal, and the whole equation dissolves just to keep the density. Right, so we are done. We'll finish up there, guys. Enjoy your weekend. See how we go.